Be talking about some mathematical ideas, and most of these are not, they're fairly standard mathematics, but they're not the sort of mathematics that physicists use a lot nowadays. We need them specially for this. However, some of the physics will start coming through a little bit in some of these ideas. Right, the first one, quaternions, and we're talking about 1843 when this starts. And William Rowan Hamilton is particularly excited when he makes this discovery, and the reason is that he realises for the first time that he's got an explanation of the concept of three-dimensionality. It was a mystery before that, three-dimensionality, but now suddenly there's a mathematics that might explain it. And what he was trying to do, I'll show you the next slide, this diagram here, the Argand diagram, forget about this axis for a minute. You've got the real numbers and you've got the imaginary numbers, standard Argand diagram, and he tried to draw a third axis to the Argand diagram. He didn't do it that way, but that was essentially the meaning of what he did. And what he found was that you can't do that. And the reason why you can't do it is because you can't find a meaning for this J. You can't find a meaning in particular for the product of I and J within the system. It just doesn't exist. We say that the system has no closure. You can find a meaning for everything except that, and that's what stopped it. However, he realised that if you added a third set of imaginary numbers, k as well as I and j, and got rid of the real axis and just had three imaginary axes, I, j and k, then you could do it. It would work. There was a way of making it work. However, there was a problem which he felt he could, what wouldn't be a problem in the end. And that was that you had to violate a cardinal principle of algebra, and that was commutativity. If A times B is no longer equal to B times A, then you've violated commutativity. And that's what happens with these quaternions. So his basic algebra was that I squared equals j squared equals ijk equals ij equals k, ki equals j, and jk equals I. So if you made the three imaginary axes cyclic, then you could do it. They would all be on the same basis then. The problem was the anti-commutativity, and we can easily see the reason for this. If we take the product ij times ji, let's take that product. Now j times j squares to -1, so we'll do that first. So we're left with I times I and minus, which we can take outside. So we got minus I, and that squares to -1, so we got equals to 1. So ij times ji doesn't equal -1, equals 1. And if ij equals k, then that means ji equals minus k. And so all the products are anti-commutative. So accepting this had to be done, he now had what we call a closed algebra. Everything worked within the system. There was nothing extraneous to it. And so for the first time that could be done. And because there are 4 units, the real numbers and then the 3 imaginary axes, we call them quaternions, which was a word that had been used. It's used in the authorized version of the Bible and other literary sources to mean fourfold things. The quaternions are double the size of complex algebra because you got twice as many units. So in complex algebra you got 1 and I, and this time you got 4 units instead of 2. Now the question immediately arises, can we do it again? Can we have another axis, even though we can't draw it? Can we imagine one? Can we do it algebraically with 4 imaginary units, I, j, k and l? Well, the answer is you can't. You can't make it consistent if you incorporate a 4th axis. That's the end of the line. That's a mathematical theorem proved by Frobenius in 1878. However, there is an exception to that. The exception is that you can do it with 1 real and 7 imaginary units, I, j, k, e, f, g, and h, which we call the octonions. However, if you want to do this, you've got to break yet another algebraic rule. You've got to break the rule of associativity. And associativity says that A times B and then multiplied by C is equal to the same as A times B times C. And if you draw up a table of octonions, you find that they're anti-associative. So this object equals minus that object, as well as anti-commutative. And you can't repeat the trick again. That's it. That's the end of the line. There is no more algebras which will fit into this scenario. So there are just 4 so-called division algebras. And you notice how norm means the product of the unit. The square of the unit is 1. The square root of the unit is minus 1, and those 3. So real complex quaternions and octonions are the 4 division algebras. And you can see how the rules slowly change as you go from the real to the octonions. You lose commutativity first, and then you lose associativity. Now the interesting thing in all this is that the threeness isn't the really key aspect of three-dimensionality of space. It's a sort of accidental product. It's really a result of anti-commutativity, and that's the thing that matters. That's the fundamental idea. The threeness results from anti-commutativity. So if we forget about the anti-associative bit for the moment, if we have 2 axes I and j that are anti-commutative with each other, then we can't draw any other axis that's anti-commutative with them, unless it's I times j. It's the only other axis that will be anti-commutative with them. And we also call that k. So anti-commutativity forces three-dimensionality. So that's why this strange arbitrary concept of three-dimensionality exists. Now, commutative things could be defined to infinity. If we had a commutative algebra, we can have as many units as we want. We can go to infinity. And we can do it without limit. And I'd like to think of it like this. Anti-commutative things know that their partners exist. So I knows that J exists and looked out for it. It doesn't know that anything commutative with it exists. So commutative things have no knowledge, as it were, of each other's existence. Now, if we take quaternions as a package, the 4 components, we will get an object like that, and W, X, Y, and Z are sort of scalar units that go with them. They're just positive or negative scalars, just real numbers. And if we take the product of that with another one of the same type, let's say primed with primed symbols, so we take A and A primed, and we multiply it out, then this is what we will get. We will get a scalar term like that, and we will get an I term, a J term, and a K term. In other words, it'll exhibit closure. We will get another quaternion. So it's an object of the same kind as the 2 objects which created it. Now Hamilton called this part, the W, the scalar part of the it is the curl. It is the curl. This is, you will recognise this from vector algebra. He called this the vector product, as I'll explain in a moment. This is the real part. He called that the scalar part of the quaternion. These are his terms. And he called this the vector part of the quaternion. So they have a scalar and a vector part. And he described this as the scalar product. We recognise this as the scalar product. If we have a scalar product of 2 vectors, it looks like that. And that's the scalar product of 2 scalars. And this here, he called the vector product. So this is the vector product of 2 vectors. And this is the product of vector times scalar. So we recognise the rules of vector algebra within this structure. He also introduced a quaternion differential operator, which he called nabla, and some people still call it that, but most of us call the vector operator equivalent del. And so he had very much the rules that we now call vector algebra, but within quaternion structure. He speculated that the real or scalar part of the quaternion wasn't space-like, it was time-like. That represented time. And the imaginary part represented the space. And so this was the long-lost link, perhaps, between space and time. And he had all kinds of strange expressions for it, like quaterno or you know, tri-dimensional progression and various things like that. He also realised that unit quaternions could be used to represent rotations in three-dimensional space. And he was completely convinced that he discovered why space really was three-dimensional, and that he discovered a key to unlocking the universe. Maxwell was interested in this. He was persuaded by Tate, Hamilton's friend and colleague. He was persuaded that he should at least do alternative versions of his equations in quaternion form in his treatise on electricity and magnetism. And in fact he did that. And so this treatise does have quaternion versions of everything that he did by the standard method. Everything looked good. This is one of the great works of the 19th century, one of the most important pieces of physics done in the 19th century. And so everything looked as though it was going to go well for quaternions, and then it all went wrong. It went completely pear-shaped. And the reason why it did was that people said, you're squaring your quaternions, you get these funny negative numbers. They square it to -1, they don't square to 1. So if you do a kind of Pythagoras theorem addition, what we call vector addition, you get negative as the result instead of positive. So it's the wrong sign of product. They also didn't like, at this stage, in the late 19th century, they didn't like the real and the imaginary parts being connected. There was no physics, as far as they could see, which actually connected them. And I think somebody called it an hermaphrodite monster, the quaternion. And so Gibbs and Heaviside formed a new vector algebra. They stripped away the imaginary part from the real part and changed the imaginary part to a real part. And they invented rules to make that possible. And those are the rules we now use, which are vector algebra. They were taken from quaternions but altered so that they would now look as we now use them. And it's a very useful algebra, I wouldn't say anything against it. It's very difficult for students to understand though, because, and the reason is that it doesn't have any logic, it's just rules. And so you learn these rules of vector algebra and you think, why on earth are they like that? They also made the scale and vector products as two quite separate operations with no connection at all. And vector algebra actually isn't an algebra. We call it an algebra, it's not an algebra. An algebra requires closure. Like you start off with the same type of things as you end up with. So there's no way you can multiply two vectors to get a vector. You can multiply is not even multiplication, it's some other operation. You can do operations between two vectors, but you don't get a vector with either operation. One of them gives you a scalar, and the other one, the so-called vector product, doesn't give you a vector, it gives you a pseudo-vector, an axial vector, for example, angular momentum or something of that kind, which transforms differently to a vector. So multiplying two vectors, even by this method, doesn't give you a vector. And the scalar product of a vector and a pseudo-vector, so if you've got a vector and a pseudo-vector, for example, space and angular momentum or something, you get another type of quantity called a pseudo-scalar, which is quite different from a scalar. So it's a bit complicated. Well, that could have been sorted out, but the supporters of the new theory decided there isn't room in town for both of us. We can't have vectors and quaternions. So they in fact had a very powerful publicity campaign and they destroyed their opponents. The quaternionists were annihilated. They were made to look stupid. One of the problems, I think, was that people didn't personally like Tate, one of the last remaining supporter of the quaternions. And so it wasn't just that these weren't ideally useful for the immediate problems we want to solve. They're no use at all. Completely pointless. Utterly worthless. Totally without application. And Hamilton's view that this must have been the most self-deluding idea of all time. And people have written to that effect and still write to that effect. That never was a great mathematician proved more hopelessly wrong. So, also, that his career had been a tragedy because he'd spent so long messing about with these pointless, silly games, silly quaternion games, that it was a total disaster. And even when relativity made the connection between space and time, no one said, well, this makes quaternions make sense after all. No one said that. even though one or two people who were supporting quaternions said it, but most people didn't. And yet, Hamilton was not only right about space-time, he was also produced a mathematics that would have removed the second objection, and the other objection was that the quaternions gave negative results when you squared them instead of positive results, like you wanted. Because he actually developed the mathematics that would overcome that. And this was almost immediately after he discovered quaternions that he realised that you could do something else with them. You could complexify them. So you could bring in ordinary complex numbers as well into the equation. So since these are distinct from ordinary complex numbers, why don't we combine the two and produce a complexified quaternions? And so we now start with not 1 ijk but 1, and the complex I, just ordinary square root of minus 1. No vector properties, no directional properties or anything, just a square root of minus 1. And multiplying everything out will also generate terms like this, and you see that I times I will be a square root of 1. In this notation you will see that anything that's bold has got this three-dimensional quality about it. Anything slanting is the square root of minus 1. Anything upright is the square root of 1. So you'll get used to it very shortly. I'll show you this. Now, let's look at these complexified quaternions. Let's look at these terms and see what happens when we multiply them out. If I multiply them out, I get I times I equals 1 when we square it, and the same with j and k. But there is something a bit unusual about this. If I take the object in the bracket as one object and I multiply ii by ij, I don't get ik, I get I times ik. Because otherwise the square roots of the black ones won't balance out. Now we can replace those units with a different symbolism, and I say anything that's upright is a square root of 1. Anything that's slanting is a square root of minus 1. If we run now, these remember are complexified quaternions, and so these will square to 1. And you may notice that these have exactly the same algebra as Pauli matrices. Sigma x, sigma y equals I, sigma z. And so effectively, these are Pauli matrices. And these have the properties that require of vectors. They square to positive values, but there's something else. Pauli matrices gives it away. And they actually incorporate spin. If you complexify quaternions, you get something that can bring in spin naturally. This is the individual who did that, the Hestoners, who's still alive. He did this in 1966, and it's quite famous. He took I, j and k as what he called multivariate vectors, sort of super vectors, as it were. And with, for example, multivariate vectors A and B had an extra kind of product. This was the scalar product, this is the vector product, but he said there was also a full product between multivariate vectors, A dot B plus I, A cross B. And when you actually work it through, this is the term that gives you what we call spin. Now Heston has shown that if we use the full product del psi for a multivariate vector del, and actually that's Hamilton's own definition of the symbol in effect, instead of the scalar product del dot del for an ordinary vector, we'd obtain spin a half for electronic and magnetic field from the non-relativistic Schrödinger equation. But that was one of Heston's great results that he got from doing this. Right, okay. And Heston has showed that the spin half effect wasn't because of the relativity that Dirac introduced, but because of the extra mathematics he had to introduce to linearize the Dirac equation. But that's his results, they're not mine. But what I would say is that all physical vectors are really vectors of this kind. That this is the true meaning of the word vector. And so when I use the word vector, I will always refer to this kind of vector. I won't refer to ordinary vectors unless I specifically say so. I will also use bold symbols for vectors as opposed to bold italics to represent quaternions, and italics for ordinary complex numbers. As I say, bold means three-dimensional, Italic, any slanting means -1, none. Now, multivariate vector algebra is a closed algebra. It has a genuine product and it has closure. And it has 8 terms. But we'll come to that in a moment. It also makes sense as pseudo-vectors and pseudo-scalars. Let's take an example. We've got a rectangle, sides A and B. To find the area, we take the full product AB. A dot B plus IA cross B. Right. The only bit that survives if they're orthogonal is A dot B. So this leaves, I'm sorry, IA cross B is the only bit. So the first time on the right hand side disappears, leaving us with an imaginary vector in a direction perpendicular to A and B. And this is an imaginary or pseudo vector because it's imaginary and it's an imaginary pseudo vector, and we call it IA, area. If we then suppose that we multiply, that we take the rectangle as the base of a solid body with height C in the direction of the pseudo-vector, then the volume will be the product IA times C, and it's the full product again. And if I write down the full product, I will get that. I think that should be C, not B. This time the bit that disappears is that, and so we're left with a scalar term, but an imaginary one. And that's what we call a pseudo-scalar. So volume is a pseudo-scalar, area is a pseudo-vector. This is completely standard in this kind of algebra. The triple product, in fact, the triple product is in fact simply a triple product. Just a product. So this time, this vector algebra is a larger algebra than quaternion algebra. It's double the size of quaternion algebra, which was already double the size of complex algebra. And so quaternions can be seen as a sub-algebra of vectors. And basically, quaternions are the pseudo-vectors. They are quaternions. Typical pseudo-vector concepts, torque and angular momentum, they're just basically a quaternion type object. And you can always transform from these vectors to quaternions by multiplying by I. Multiply vectors by I, you get quaternions. Multiply quaternions by I, you get vectors. And if you do vector algebra in this form, it incorporates the 4-vector algebra of relativity. And it's equivalent to the complexified version of a quaternion. So if you complexify that, you get that in principle. It doesn't matter if it's plus or minus. If you complexify that, you get that. Now, the most remarkable extension of this comes with the algebra invented by Clifford in the 1870s. And Clifford, by the way, first wrote down that expression. He didn't use the term multivariate vectors. It's also called geometrical algebra. The terms are interchangeable. And I think it's about the most powerful tool that physicists could have. And it's used by some physicists, but nothing like enough. Dirac realised early on that his own algebra was a version of Clifford algebra, but he never wrote it out in any other form than the matrices, to my knowledge. This algebra unites anything like real complex numbers, quaternions, vectors into a single system, and you can also do a version of it using octonions. So effectively a Clifford or geometrical algebra, which we write as CLM, n or Gm, n, has m units which are square roots of 1, null 1, and n which are square roots of -1, and you just then make up the algebra that will do that. In fact, if I was to say Clifford or geometric 3, 3, that wouldn't necessarily be unique. I could possibly do it in a different way. It's often possible to change one particular algebra into different specifications. Now, one way you can build them up is to use cubiting sets of quaternions, which I've just mentioned. You can just have endless sets of these quaternions. You can have 5 sets of quaternions and make an algebra from them. Or you can have complexification as well. Now, this is the complete algebra that's for 3-dimensional space. This is one 3-dimensional space, looks precisely like that. It has 3 real vector terms, 3 complexified vector terms, complex numbers and real numbers. And those together make the complete algebra. And that's the only way you get closure, if you include them all. And they have different names. You can call that a vector. This one is a product of two vectors, it's a bivector. That's a product of three vectors, it's a trivector. That's a scalar, of course. But you can call that a pseudovector or pseudoscalar, and you recognise, of course, that's equivalent to a complex number, and that's equivalent to a quaternion. So they're just different versions of the same object. To specify, now if you look at that, you can see that this is the, I could get the complete algebra just from those. I don't, because of multiplication of those, if I kept multiplying them, I'd get the complete algebra. But I could also get the complete algebra out of any of these three subalgebras. So you see there are three subalgebras. This is a subalgebra, that's another subalgebra, complex numbers, that's quaternions, and that's scalars. They're subalgebras of the complete algebra. And I'm just mentioning there that we use the terms bivector and trivector. Now, what I want to do now is to say, let's take two of those objects. That one, that's space. If I were to specify the complete structure of space, including all its areas and volumes and all that stuff, that would be what it looked like. That's the complete algebra for space. Let's suppose I had another complete algebra of that kind, and I'm using a different colour coding, to which that was commutative. So I've got two such algebras, I've got that one, and I've got that one, and they're commutative, and I'm using colour coding to distinguish them. Now what happens if I make an algebra out of those two combined? I get 64 units. 32 plus and minus. So you can see this is the first space. I don't need to repeat those because they're commutative. That's the second one, and then this is the combinations of the two. That's what it would look like. And there are 64 units, and 64 immediately rings a few bells. 64, Dirac algebra, Dirac equation. That's where the word 64 comes into an algebra. And so, in effect, this algebra here is an algebra of two independent spatial algebras, two spaces together. That's what it is equivalent to. This is lots of quaternions. It doesn't make any difference because I've got complex numbers there, so I will get the equivalent to that from that. I can also do it using one set of vectors and one set of quaternions, as long as I've got the complexity there. Okay, so those three versions are exactly the same. In fact, this is the one I am most interested in, but those three are the same. Now, I was going to say that the same algebra can have different dimensionalities. This is a very interesting aspect of Clifford algebra, that the same algebra can have different dimensionalities simultaneously. It depends how you distribute between m and n. For example, 2 square roots of -1 could be considered 2 dimensions, or they can be considered 1 dimension, because they join together to make 1 square root of 1. So, depending on how you distribute between m and n, you can do the same algebra in different dimensionalities. So I'm saying a thing that could look like 10 dimensions in one perspective and 3 dimensions in another. That's what the point I'm really making. But 3 dimensions is certainly special. And any higher dimension, if you don't go down the anti-associative route, can always be resolved into structures based on 3 and complexity. So higher dimensions within this algebra are always based on 3s. Right, I want to do something different now. Groups. Now, many people know a lot about groups, but a few people perhaps haven't seen them before. A group, I'll define a group. I'm interested in particular groups, so this is why I brought this up. A binary operation, in other words, for example, multiplication. A group has a number of elements, say, and each element has a capacity to have an operation with another element. So it might multiply it, or it might add it, it might do some permutation or something. So that's what we call a binary operation. And the 2 elements will always produce another element of the group. There has to be an identity element, so if you do a binary operation between one element and that identity element, you get the other element. So if I do A and the identity, I get A. An inverse to each element, so the binary combination of elements and its inverse produces the identity. And closure, so nothing new happens. So any binary operation simply produces another element in the group. This is the simplest group, C2. Order 2 has 2 elements. For example, plus and minus 1. Binary operation is multiplication, identity element is 1, each element is its own inverse, and we have closure because whatever binary operation we do, we only get 1 or minus 1. So that's a good example of a group. This is complex numbers are another group. There's a group of order 4 called C4, made out of the base units 1, minus 1i, and minus I. And you can work through that and see that it obeys these rules. It's a good example to work through. Quaternions are a group of order 8. Those are the base units of quaternions. Multivariate vectors, a group of order 16. And you need negative as well as positive units for closure, as well as for quaternions. Octonions are not a group. You can't have a group if you've not got associativity. So octonions are not a group. Now, an important aspect of groups, a very important aspect, is that you don't need all the elements to specify the group. You need a fraction of the elements, a number of the elements. And we call that generators. So within a group, you can choose a number of generators which will generate the entire group by the multiplication. And that's going to be very significant. We'll talk about that in a moment. C2 and C4 are cyclic groups. And this is what is an example of a cyclic group. You have an identity, then you have, say, something like A. You have A squared, and A to the n, and A to the n goes back to I. So if this is group of order 3, cyclic group of order 3, and A cubed is the same as the identity, so that's how it works for the cyclic group. There's a cyclic group of order 4, and this is a cyclic group, the one we've just mentioned, complex numbers. And in that order, that's equivalent to A, that's equivalent to A squared, that's equivalent to A cubed, as you can see. However, there's a second group of order 4 that's not cyclic, and this is a much more important group than the cyclic group. It's called dihedral 2, D2, because it's the group of rotations of the rectangle. It's the identity and the 3 possible rotations in different axes. It can be generated by a double algebra known as H4. And this can be constructed from 2 sets of quaternions. And I'll show you that in a moment. If I write down the table for this group, then if I combine 2 quaternions, II, JJ and KK, then this combination is now commutative. There's no minus. If I multiply II by JJ in either order, I'll get KK. And this is the group table for the D2 group, the H4 algebra. There's other ways of getting it, and this is a more important way for us, well, an equally important way. This is a different way of getting it. I've got 4 elements, A, B, C, and D, and I give them each 3 properties, which X, Y, and Z, and the minus X is a kind of anti-property to X. And a binary operation doesn't have to be multiplication, so we'll make up a new one. We'll say that if the property has the operation on itself, then it produces itself. If it operates on its anti-property, it produces the anti-property. If it operates on a different property, it doesn't produce anything. And that will produce as a group table. We'll do more of this later. Which is identical to the one that we had previously. It's identical to that one with these, but by a different group. You see, that's the same group table. This is a very important group. I'm sure that, in my view, that's the most important group in the whole of physics. It's a very simple group, but it's the most important. We can also arrange a dual version. Here I've swapped the x's round. I've swapped the x's and minus x's, and you can see that it doesn't make any difference to the group structure. It will still look the same. Now, let me go back to this algebra I had previously. This one here. This one. That one there. I said there were plus and minus of those 32 terms created the entire algebra. Now this algebra is also a group. It has all the properties that a group would have. And this is included the minus terms as well as the plus terms and arranged them in a different order. But that's the same as what we showed before, and that's the minus terms. Now I want you to look very carefully at that, because this is incredibly important for physics, this group. Now if I look at that line there, that line of elements there, and I took the trouble to multiply them out in every possible combination that I could, it would generate all of them. So these 5 here are generators of the entire group. As are those 5, all those 5, or any of those sets of 5, there are 12 different sets of generators for the group. I only need one of them, I don't need them all, to generate the entire group. And this group requires 5 generators to generate it. So it requires any of these. Then there are other versions of it, but they all look very similar. I'll explain it in a moment. So if we ignore the complex algebra part of it, then the rest is forms themselves into 12 groups of 5, which are each sets of generators of the group. Significantly, they all have the same structure. Let's have a look at that structure. I'm going to build it up for the first line. Okay, I'm going to build up the structure for the first line. If I start with this object here, I've got complex I, I've got 3 vectors, I've got 3 quaternions, and I've got the real number that goes with quaternions. I then take, you follow this very carefully, I then take one of each of these red objects and just arrange it underneath like that. Don't ask me why I didn't put I there, it's historic, that. It's just the way it's worked out. And I now combine that with that, and I get IK. I now combine that with that, and I get each of those 3, and I get that. And I combine the J with the scalar, and I get that. Now this, you will recognise, is equivalent to the first line of the generators. So those are generators of the entire group. But what I want you to notice very carefully is the difference between the red and the blue. The blue parts there, you will see that these blue objects here, these 3 blue vectors, are each attached to exactly the same object, a red I. And you can see that these have a symmetry preserved. There is a preserved symmetry. So the symmetry between the blue objects isn't affected by the operation I've done. They're symmetric with each other because they're combined with the same type of object and not a different one. Now look at the red objects. You can see that this is connected to a pseudo-scalar, an imaginary number. This one is connected to 3 vector operators. This one is connected to a scalar quantity. And so in that sense, you can see that I have broken the symmetry of the red ones. They know in that structure they are no longer a perfect symmetry between themselves. So in creating this group, I've had to break the symmetry of either that or that 3-dimensional operator. And that's a very crucial point. That's just purely mathematics, but it means that to get to the minimum structure I can, I've had to break the symmetry. And I could have done the same had I used 2 lots of vectors. You see, if I'd had 2 spaces, 2 actual spaces, I would have had to break the symmetry of one of the 2 spaces to get the generators for the group that combines them. So to find the minimum structure from which they can be generated, I would have created a broken symmetry for one of them. And now in the last lecture we said how broken symmetry always resulted from complexity. And this is a kind of first level complexity, a packaging of all the objects. So if I had 2 such structures, I would have broken the symmetry between one of the 2 component 3-dimensional objects. Now this is very familiar to physicists. I don't really want to dwell on this. I think I'll probably leave most of this out because this is Lie groups. There are groups that contain infinite numbers, and 3 that are very important to physics are U1, SU2 and SU3. And the U1 symmetry is essentially equivalent to rotating a vector or some object in a circle like that in the Argand plane. And these numbers, the numbers along this, correspond to the members of the group. That's just one version of it. So that's an important one. In the U1 group is a group with one generator. It's got an infinite number of component members, but it's got one generator. The U1 group is the one that's connected with the inverse square law of force, and the one generator in quantum physics is the boson, which is called the photon, the mediator for the group. But that's standard physics. I don't want to talk about that particularly. You can read about that in the text. And the other two important ones in physics are the SU2 groups, SU2 and SU3. SU2 groups can be defined, let's see how that's defined. U groups are defined by matrices. A SUN group is defined as, they've got n squared minus 1 generators. They are defined by the unitary matrices, which unitary matrices of determinant 1, which of that order. So if you've got SUN and n is 2, then the matrices are 2 by 2. If it's SU3, then the matrices are 3 by 3. But that's standard physics. In standard physics, SU2 is the group for the weak interaction. The three generators are called WS, W minus, and W0. And the first two are recognizable as the weak bosons, and the third one combines with the U1 field to produce the Z and the photon. I'll leave you to look that up in standard physics. SG3 is the symmetry group of the strong interaction, and again that has n squared minus 1 generators, which is 8, which are identified with the gluons involved in that interaction. All the groups involved in physics, in my view, can be derived. Well, I know that they can. All the groups of interest in physics are known to be derivable by the symmetry properties, the rotations and the like of the real numbers, complex numbers, quaternions and octonions. All the important groups in physics, SU1, SU2, SU3, U1, and even the bigger groups, F4, E6, E7 and E8, are all dependent on these fundamental algebras. They're all aspects of those algebras, and that's a well-known fact. This is going to be more important to us immediately, and I'm going to talk about nilpotents because these will come into what I'm talking about. Nilpotents are objects for which any repeated operation eventually produces 0. You can get them with upper triangular matrices, for example. You just gradually reduce the matrices till the matrix becomes 0. But we are concerned with one particular case where the operation is squaring. So in other words, a nilpotent in our definition is the square root of 0. And of course, 0 trivially is nilpotent itself. However, you can easily create nilpotents that are not 0 themselves. For example, any Pythagorean triplet can be represented as a nilpotent. If I use my operators here, ik, and I have 5 there, and I have I there, and 4 there, and j there, and 3 there. When I square that, all the cross terms, the 4s times 5s, 3 times 4s, will all disappear because you get plus and minus versions because they're anti-commutative. Whereas the squared terms will remain. So that will become 5 squared, minus 4 squared, and minus 3 squared, which is 0. And it can represent any Pythagorean number that way. This one here is slightly different because I've now made 4 into a multivariate vector. And this is what the physics looks like. So you've got an extra concept here, which is 4 is not an ordinary number, it's a multivariate vector. But even so, it still becomes 0 in the same way. And another concept which is important is an idempotent. And this may look complicated, but all I'm trying to do here is show that you can find an object which multiplied by itself gives itself. So not a squared equals 0, but a squared equals a is an idempotent. So given a nilpotent, you can usually create an idempotent from it. And if I've given that is a nilpotent, I can make that into an idempotent by multiplying it by k in front and dividing by the square root by 10 of 10i. And you can do that as an exercise afterwards to work out that it just produces itself. I'm just showing how to do that.
It must be some kind of unit.
It's a kind of unit, yes. It does have a physical meaning, but we will come across that. Now I want to say something about real numbers, because this is important to us too. You will be familiar with the idea that you've got real numbers, you've got natural numbers, 1, 2, 3, you've got integers, plus and minus of those, you've got rational numbers when you divide them, you've got algebraic numbers, which roots of equations like x squared minus 2 equals 0, and then you've got transcendental numbers like e and pi, which you need an infinite series to generate. Now, Cantor has a very famous argument saying that the rational algebraic numbers can be counted by putting into one-to-one relationship with the integers. You can map one-to-one onto integers. But the transcendental numbers, so the real numbers as a whole, cannot. And what he says is that between any two numbers that can be counted in this way, there are an infinite number of real numbers that can't. So the real numbers are uncountable or non-denumerable. Now this is a true argument, completely valid, and most people think that it's uniquely so. But in fact it isn't uniquely so. It's true, but it's not unique. It's not the only construction of real numbers you can have. So even though it's valid, it's not uniquely true. Real numbers can be constructed in such a way that they can be put into a one-to-one correspondence with the integers. It's all the famous old question, what is mathematics? Is it there, or do we find it? If we define mathematics as being there, then Cantor's argument is true. If we define it as being what we find, then it isn't. Because if it has been shown a long time ago that if you define real numbers that way, and Skolem did it in 1934, in what is called non-standard arithmetic, you can put the real numbers in one-to-one correspondence with the integers. It's a very surprising result, but it's true. And there's a theorem which Skolem was part author of, in which any consistent finite formal theory is a denumerable model, in which the elements of its domain are in a one-to-one correspondence with the positive integers. So if you could devise an algorithm, you can count it. That's the bottom line. In addition to real numbers in arithmetic, there's also a non-Archimedean geometry, which is exactly a geometric version of this. There's also a non-standard analysis, which is a calculus version of this. Now, we taught differentiation using infinitesimals. Everybody learns it this way. You have a graph and you have 2 points separated by delta x and delta y, and you use the formula for the graph to find an expression for delta y over delta x. You then bring the points closer together until they become 1 point, and delta x tends to 0. And in the meantime, you've cancelled out all the delta x's, delta x squared, and all that. You call those that's the method of infinitesimals. And this method was around in the 17th century, and eventually, when the 2 points coincided, you call it dy over dx. The most familiar form of it is that by Leibniz, and it was always considered, when I did mathematics, to be a bit, okay, it works, but we don't like it because it's not rigorous. To do it properly, you had to take the limit. Now, Newton, who looked at infinitesimals and done some calculations with them, didn't like them, and he invented a process which is similar to what we have as a limit. However, the process was perfected by Cauchy, and there aren't any such cancellations in this method. In the 20th century, Abraham Robinson has actually shown that using the method of non-standard analysis that you can use infinitesimals in a totally rigorous way. And funnily enough, he uses nilpotents. This non-standard procedure, the standard procedure, are exactly the same in results. Each produces the same number of theorems, same proofs. They're not identical proofs, but they're equivalent. And also, you can't tell which is going to be the easier method to use. It could be one or the other. It's arbitrary. We don't know until we've done it. You can't tell in advance. So neither is superior to the other. They're completely dual, in fact. So that will be an important point I need. I need that very much. I also need a little bit of topology. This is the only bit of topology I need. Though I use topology in areas I'm not going to talk about. I want to distinguish between two things, a simply connected and a multiply connected space. A simply connected space is just ordinary space. If you go circuit round a simply connected space, if you took a vector around it, parallel transport it along the tangent, you'd find it pointing in the same direction when you got back to your starting point. However, this one is a multiply connected space. In other words, it's got a singularity in it. And if I were to do the same thing with a vector around this one, I'd find it pointing in the opposite direction. And that's a very well-known result in topology, and it's connected with a physical phenomenon called the Berry phase, in which you get, if you've got a singularity in the circuit, then you end up with a 180 degree or pi phase change. So I think I've explained that there. And that's all I want to say about that. I'm just introducing these topics. The relevance of them will come when we actually talk about physics. And what I want to say here is, this is really, looks quite trivial, and it is, but it's also very profound. And what we notice is that a few key integers turn up all the time in physics, and even in other areas of science. And these are incredibly important, and they're 2, 3, and 5. And when we ever find 2, we can be absolutely certain where the origin of it is. It's duality. It's some kind of duality. Wherever we find 3, we can be certain that it's anti-commutativity. And where we find 5, there's the alarm bell rings there, and that's symmetry breaking. So 5 is a complex concept, but 2 and 3 come from a really primitive level. Nearly all the group structures that are important in physics, even the really complicated ones like E8, are just versions of 2s and 3s put together. And you can track them all down to dualities and anti-commutativities. There's nothing more in it than that. Okay, we just about made it. Okay, thank you.
Thank you.
So, what I'm proposing is that the thing that we call spin will emerge naturally out of the algebra. It's not me who's proposing this. This is done long before me.
The degrees of freedom in this algebra involve something now which is non-commutative.
If this algebra had been followed through from the beginning, what would have emerged is what we now call spin. As a natural result of the algebra, and that is the same as the spin that we use in quantum mechanics. That's what I'm saying.
I think it's the words infinite potential complexity that might stop people.
Well, what I mean is that you've got any amount of these systems you can join together into a larger system. You can have one that just deals with three-dimensional space, and then you can go to any dimensionality you want, is what I mean.
I'm sorry, I've got to interrupt now, because I've got stuck in my mind your earlier statement that we could only have quaternions and octonions.
That's within one system, but you can have an infinite number of systems. You can have an infinite number of quaternion sets, as long as they're commutative to each other, or of vector sets, as long as they're commutative to each other. So you can do it to infinity.
You've got to be very careful. I mean, there must be a lot of technique behind this that you're not covering, but you made a very clear distinction earlier between using square roots of -1 in terms of complex units, in terms of quaternion units, and now we're using these. So there must be rules underneath there.
Oh, there are
how
rules.
you to sometimes do it and sometimes not.
Yeah, there are.
I think we need to be...
Yeah, there are such rules, but I can't deal with them entirely here.
Hey, doesn't the identity have to be unique?
Identity.
Squares to itself is...
Yeah, but that's not identity. Squares to itself becoming one doesn't mean it's identity. I know, I'm not saying an idempotent is a group.
Okay.
That's only a group.
Yeah.
Yeah, that's only for a group. It's not a group.